Okay, so a quick video about observations and data. I want to go over observations because as you're getting just started into high school science, observations is absolutely everything when it comes to doing really good science experiments and also making good discoveries. It's the people who are the most observant that often make the greatest discoveries, for example, and also the greatest work when the students are doing their assessment pieces as well. They really observe it. Now, when you hear the word observation, I think you're all thinking of like things you can see. You're thinking of your sight. Okay, oh, there's a book over there. It's colored red, and it's about this big. And you're giving me some information, some observations based on things you can see with your eyes. However, I need you to broaden that horizon there, is that there are other things that you can detect using all of your main senses. Now, I've just got the main sort of famous five here. So things you can see, smell, touch, taste, and hear. But there are other ways of sensing the world around us as well. Like, I think we've all had that thing where you can feel when something is off balance, for example, or you're about to fall over, you can feel that. Okay, so it's not one of these traditional five senses. There's more out there if you just think about it. But here I've got Chemistry Cat. She is setting fire to her science textbook here, and she is using a magnifying glass to make some observations. Now, if we imagine what things she could be detecting from that perspective, so things that she can see, she should be able to see that there is a book, there is a fire, it's on the ground, there is smoke. The fire is bright, the fire has a bit of an orange sort of color to it, the book is black. The corners of the book seem to be glowing red and a bit of orange, maybe a little bit white in some places. The paper seems to be shriveling up as the paper burns. So these are things that she could notice just by using her eyes. If we think about things that she could detect right now with her sense of smell, she should be able to smell the smoke, possibly the smell that fire makes. She might be able to smell the magnifying glass that she's holding in her hand and also her smoking pipe that she's got next. I was supposed to draw like the Sherlock Holmes hat, but I forgot about that feature. So it was supposed to be like a little Sherlock Holmes for like making observations. So those are things she can smell. What else? Oops, that's the wrong button. Let's go to touch. So what things could she notice through touch? Well, I don't think she's going to touch the book or the fire or the smoke. So in this occasion here, touch would not be one of the main ways that she could be making observations. Although if she really wanted to, she can go and grab the book and burn her fingers. What about taste? Again, she's not going to taste the fire. Well, she hasn't. Maybe she can taste the tobacco from the smoking pipe that she may have been using as a prop. My wife was thinking that maybe you should just blow bubbles rather than actual tobacco, which I think is a lot cuter. I think the other one here that she can get right now is hearing. So when she's standing this close to the fire, she should be able to hear the crackling that happens when you have a fire. She probably can hear a bit of the movement of air, because as the fire burns really vigorously, you can hear the air move in quite quickly and carrying away the smoke up as it flies upwards. So these are all things that you can be making observations about. Now, this is, I've just written in some observations that you can make using yourself, but keep in mind that you can be using technology. I just wrote here like a machine, so she could be using, instead of a magnifying glass, she could be using one of those infrared cameras, those infrared guns, and she could be pointing at the fire and actually getting an actual numerical reading of exactly how hot the fire is. She could also have a different device in her hand that could measure how much light is coming off of that fire. She could stick a thermometer into the book. So she could put like one of those digital thermometers and stick it into the pages of the book to see how hot it is on the inside. She could maybe have a detector for how much smoke particulates are in the air. So there are other observations that can be made when you're using a machine. Okay, and that's just a list of examples of things I've written in here that she could be observing. So if we make good observations, we can do good science. Because that's basically what we're doing. We are often trying to understand what's happening in the world around us, so we can discover the natural laws, how the world works, how nature does the things that it does. We come up with predictions or a hypothesis. We think it behaves like this, according to this sort of rule. And then we conduct a test to see if the evidence matches what we thought would happen. And if you do this many, many times with different people and we're all trying to test the same idea from different angles, different methods, and if we all basically find that, hey, that idea that this chemistry cat had about how fire burns, you know what? We think she's onto something. Apparently, when you set fire to a book, it turns black and it burns. So it all comes down to observation. So here's some other ones. We might be trying to test, like, okay, well, why don't we have, like, if we got electric cars and we got solar panels, why don't we just make an electric car that can recharge itself with solar panels on the roof? Surely we can do that. And so we would go and maybe build a prototype and then measure it or make some observations to see, well, can it be done? Is it going to be strong enough? That's where observations are going to be really critical to finding out to see if our idea was going to work out or not. Another one here is, I'm sure you've all had some experience making paper airplanes. And so often you are trying to make the paper airplane that'll travel the furthest. And so there's many different ways you can fold the paper, and ultimately your goal is to see how far it goes. So you're often making an observation. You think maybe if the wings are really, really wide, then it floats better, so it flies longer. And so you build a bunch of paper airplanes that have really broad, wide wings, and you throw a bunch and you make observations. How far did it actually go? This one traveled the furthest, okay. That seems to go against my original idea, so maybe it isn't just about making really, really wide wings. Maybe it's about these little structures on the corners. Maybe that's what's making them fly better. And you do some more tests and you do some more observations, and you basically keep doing this process where you use the previous observations to inform your next experiment. And you just keep doing that and keep doing that, keep doing that, and that's how we get a lot of our modern understanding of science and how we get to our modern types of technology as well. So, it's critical that we make good observations, as particularly unbiased as possible. So unbiased. So bias will be things like where, because we are human, we have weaknesses. For example, if you didn't sleep well the night before, and then you come into the office and you need to do some experiments and make some observations, well, because you're sleepy, you may not be as aware of the surroundings, and you may miss things in your observations just because you're too tired, or maybe you are distracted, or you other things like that. Or sometimes things can appear but they aren't actually. For example, if one famous example of how bias can affect how you make observations as a human, I think there was an experiment where they had some footage of some kids playing at a playground, and these parents were shown the footage, and they were saying that these children had just had some cordial before they went out to go and play, and they were asked to make observations about how the children's behavior was like. And the parents were saying, oh, they're super hyperactive, and using that type of terminology. Whereas they did the same experiment where they showed the same footage to some different parents, and they didn't mention anything about cordial at all. And then those parents described the children's behavior entirely differently. They didn't necessarily use words like hyperactive and things like that. The bias is that we often have this attribution between cordial and sugar drinks and small children going, extra active, hyperactive. And that if you have that if that's part of your worldview, then you're going to make recordings that matches that. It's going to be influenced whether you are aware of it or not. So how do we conduct experiments where our human flaws are not going to be um, a, um, part of it so much? And that's going to be using as much technology as possible, which is why a lot of science experiments, investigations out there in the world are probably very expensive because they have to get special equipment. For here, we got a crash test dummy. Now, if we just did this by human observation, we would have the car, it slams into some object, or some object slams into the car, and then you would stand there and you would try your best to observe what happened to the crash dummy. Now, because this is happening so quickly, the observer, the human observer, may not notice this hand maybe is colliding with the windshield, for example. But it's just a microsecond, but it was so quick that the human observer didn't notice. So what do we do actually in the real world? Well, you can see there's a bunch of things all over the crash dummy in the car, and these are going to be usually markers for a camera. So this, obviously, this image has been taken with a camera, probably a high-speed camera, and that way it doesn't require any human intervention at all. You just turn the camera on, it does what it's always does, it just records information every, many times per second, and then you can watch the video playback. You don't have to be limited to how quickly somebody can track their eye on a very fast-moving object. Another one here, this looks like some sort of electronics, and what they've got here is, this is a thermal imaging camera. So if I said to you, like, oh, does this wire feel hot to you? And you might hold onto that cable, which is going to be this bit here. And you might hold onto that cable there and go, yeah, that's pretty hot. But I was like, is that too hot? Is that within safety mode? Is that within spec? Okay. That's going to be difficult to judge if you're just holding onto the cable with your hand. Now, it does look like it's about 75 degrees Celsius, so let's be honest, your skin would just burn. But if it was something more respectable, like, 40 degrees Celsius, you may not be able to sort of tell, oh, that feels about 40 degrees Celsius. You would have no idea, no frame of reference. So we would use a machine to take a measurement. So you could put a thermometer straight into the cable somehow, or you can use this thermal imaging camera, which takes an image of the whole view, and it gives you a bit of a number scale here to give you an idea of exactly how hot it is. It's not requiring a human to sort of guess what the temperature is of that cable. So that brings us to a little observation. Now, I would normally run this with students. We'll put candles out, one per bench, so that each group can sit around the candle. And the challenge is that you as a group or as individuals, if you like, and that's what I'm going to ask you to do right now in a second, and you're going to pause this video, is to make as many observations as you can about what you can see in this image below. Keep in mind, this is just a video image here, so you might have to make up some of the things that you would experience if it was a real candle in front of you. So, for example, I think you would, if the candle was in front of you, you would smell. You would smell the candle wax. You might smell if it was like a scented candle, maybe. You might smell the smoke or that smell you get off of a freshly lit match. These are things that you would have to write about in your observations, but without actually experiencing them firsthand. I think I challenged the students that, in the past, Mrs. Holt's class got the most observations for this candle experiment here. And I think last time the students got something like 40, 60 different observations. They just sat there writing down everything they could notice about the candle in front of them. Here, there's a bit more things for you to munch on. So there's other things in the background that you can write about. But bear in mind, it could be things you can see, smell, taste, feel. What else we got here? Here. Okay, so don't just be limited to things that you can go deeper. Like, for example, I won't use this image because it would take away some of the fun. Make some observations about this picture here, okay? So I'm just going to go over things I can see. I can see there is a car. I can see there is an airbag. I can see there's smoke. I'm not telling. I can see that the crash dummy has some stickers on its head. I can see that its neck seems to be some sort of different material. I can see that this crash dummy is wearing some sort of red suit. I can see that there's some, looks like they've added some extra sticky tape markings to the door for some reason, not sure why, but there's some extra tape there. I can see there's some sort of code stamped at the side of the vehicle, perhaps for identifying the video footage or maybe the vehicle type itself. I can see that the door is closed. I can see that they've also got lights in the background. There's, let's see, 1, 2, 3, 4 different light banks in the background. I can really nerd out and say, okay, these all look like they're tungsten equivalent light bulbs here. So what else can we see? There's a seat belt being engaged. It looks like this is a left-hand drive vehicle. This vehicle seems to have an indicator right on the side view mirrors. Look, there's so many things we can make observations about. So there's going to be even more things like, remember we got feel. So although I can't feel in this image, we can make some generalizations here. I think you would agree that the paint here would be very smooth and maybe glossy, and then maybe this fabric here might be a bit maybe a bit coarse fabric. Perhaps they're maybe not making out of silk. I can probably make some judgment calls about what the airbag, maybe it's soft, probably is soft because of what it's supposed to do. Probably make observation here that these lamps in the background are probably very, very hot just because of the way that they work. Yeah, so think about texture as well. So how would it feel like in your hand? Is it smooth? Is it rough? Is it cold? Is it warm? These are more things you can add to your observations. So you can have it a go. So I'll pause it. I'll just pause for a few seconds here, and I will finish the next bit of the video in a second. If you hit pause now and try the challenge. Maybe give yourself maybe 10 minutes. I think the other class took about 10 minutes to get a decent amount of observations. Okay, obviously I'm not going to make people on YouTube wait 10 minutes, so I will continue talking. So you have the power to hit the pause button and do the whole 10 minutes, but I'm going to carry us on forwards. And that is, we're going to talk about types of data. Okay. Did I spell it right? I think I may have spelt this one wrong here. Yeah, I think I put too many letters in here, my apologies. But we've got different types of data. So when you make your observations and you write them down, which is the critical part for science, don't just like make them up in your head. You need to record them onto paper or record them in some way. When you do this, you will typically find that the types of things you notice, your observations, they can either be a qualitative bit of information or a quantitative, meaning a number. So qualitative data will generally be things like, okay, what color is it? What does it smell like? Does it feel dry? Does it feel wet? What kind of consistency does it look like? These are things that can't be described with a number. You know, oh, that bit there is really rough. That bit there is very smooth, for example. Those would be qualities. Other qualities could be some really generic things like, oh, that was very quick, or that was very slow. It was very hot. It was very windy. These are qualities, but they're not a number. So they're not as precise, but they are useful to know. Don't just ignore qualitative observations because they are often, when you conduct experiments, let me just go back to this one here. When you conduct experiments like this, and let's say that some of the results are different from what you expected to happen. Like you did all this engineering, and so the crash dummy should have behaved this way. But yet, when you see the actual crash test, the crash dummy moved or behaved in a different way. Why? Well, if you've made a lot of observations like we just did here, I think you basically start to build up some clues that may explain why the results are a little bit different than expected. So it's not to say that qualitative data is not important. It absolutely is. I find they're most useful to me when I'm trying to explain why things didn't work out the way I thought they were. Quantitative data, which is the green stuff here, These are going to be things that you can measure with numbers. For example, how heavy something is, how fast it's moving, exactly what temperature something is at. So anything with a number. I can't think of any more right now, but I'm sure you can think of other things we measure every day with numbers. But this is our main preference in science because it's less likely to be influenced by our bias. Like I said earlier in the story about the cordial, people have they have a preconceived notion that cordial makes students who are very little very hyperactive, which may or may not be true. With numbers, it's very difficult to have bias in that. Sure, you could probably rig the experiment to give you false numbers. There's one way of doing it, but we all strive to try to get the most accurate and unbiased results as possible in science. That's our main mission. So, for example, if I really wanted to find out, does red cordial make students more hyperactive, then I can't just watch video playback of students, people playing around, because it's all very random. And maybe, what if it's only slightly more active? How would I notice? Maybe it's so slight that I don't even notice. So what's a way I could measure it using numbers rather than trying to sort of figure it out by eye? Well, I think one thing you can do is that on your mobile phone these days, Here's what I found. Oh, hello, Siri. On your mobile phone, they have sensors that can detect when you're shaking your phone. Okay, there's a little measurement device in there called an accelerometer. It measures changes in acceleration. So if you are suddenly standing still and then you start running, that's a change in acceleration, and so the device would notice that. You may see this manifest itself if you've got a smartwatch and you lift your hand and turn your wrist so that the watch is now facing to your eye. You may notice that the watch actually lights up. The screen turns on. It's using the accelerometer to signify, oh, this person's turning the wrist over now. That must mean that they want to look at the screen. Same thing when you pick up your mobile phone off the table, the screen wakes up. It's using the accelerometer. We could put one of those devices onto some sort of child who's had, a full meal of cordial, and then we would just let it take measurements as they're playing around in the playground. We can get some measurements of how much they are accelerating, decelerating, standing still, get some measurements off of that, and then compare that against experiment where the students had no cordial and see if the numbers are different. If the numbers are higher or more activity in the cordial group, then that would give us some confidence that maybe there is something to it. If we find that the numbers are roughly about the same as each other, then we can probably say that there doesn't seem to be much connection between the cordial and hyperactivity. So, we are often looking for quantitative data. More about how our human perception can be fooled. Well, these little magic eye experiment things here are basically that, where your brain can, if you cross your eyes hard enough, you can start to see things that aren't really there. I just got a picture of a police car. It's not really that important about the police car, but I do recall a story that Neil deGrasse Tyson would tell frequently about humans being flawed with making observations. And he was saying that he's a science astronomer, and so he has a really big thing about people claiming they've seen UFOs. And so he gives this example where this police officer was phoning in to, I don't know, he was phoning in somebody saying, I've just come across a UFO. It's right above my head. It's darting back and forth, back and forth, back and forth. And then Neil deGrasse Tyson, who's telling the story, is saying that what he's actually looking at is the brightest star in the night sky, which is Venus, which doesn't move very much at all. And the fact that he's noticing it darting left and right above him on the sky is because he was driving on a windy road. So, but to him, he was making observations, him or her, and they were flawed because the car was obviously traveling on a windy road, and that can change the way that things are viewed. Whereas if the person had stood outside the vehicle, and looked at the night sky, I think they would probably notice it's not moving that much, whether it was a UFO or not. Okay, I will end the video here, and I hope that in future lessons we can move into how we can record our observations, particularly numerical observations, into tables and graphs.